at the derivatives and integrals of vector function, and I think we got by the idea that if you want to differentiate one, don't you just differentiate each individual term? And if you want to integrate it, you just integrate each individual term. So let's add some more things to that list. Right, let me pick a nice simple function to start off with. I'll keep it as polynomials. So I have a t cubed, 2t plus 1, and 3t squared plus t, right? And I would like to know at t equals 2, a vector called that guy. And he is called the unit tangent vector. Unit tangent vector. Very often just called the tangent vector, or t. Now, the term, or that term there, unit, doesn't that tell you that this vector is going to be a 1 unit long, right? It's going to be a unit vector. And what does it look like? Well, it looks like this guy. It's the derivative guy turned into a unit vector. Do you see how dividing by the magnitude of it makes it half? So that is essentially the formula that we'll use to answer these kinds of questions. So I'll start off with the guy that we've got. I'll find his derivative. Differentiate that guy, 3t squared, differentiate that guy 2, differentiate this guy, 6t plus 1. And since we're interested in the answer only at 2, to make our life simple, we'll find the derivative at 2. So that's 12, that's 2, and that's 13. And so won't the unit tangent vector, at 2, just be, well, I guess I forgot something, so I might as well do it now. Don't I need to find the magnitude of this vector? So it's going to be the square root of 12 squared plus 2 squared plus 13 squared. No way I'm doing that in my head. So 12 squared plus 2 squared plus 13 squared, and I get 317. So the unit tangent vector at 2, let's move him a bit lower. This guy, he is 1 over that guy, 12 to 13. Since this guy is not very pretty, I can't really simplify him, at least I can't see any obvious way to simplify him. I get that guy. So far, so good. Right. I would, since I randomly just picked one, can you imagine that these numbers might be nice the next time? You know, for instance, that might be the square root of 36 and be 6, right? Or at least something like 8, which you could at least work with. But nonetheless, the process doesn't change. So what does this fella look like? Well, if you imagine your typical space curve, and let's suppose that at this point here is t equals 2, then your tangent vector would be, right, that guy. That would be r dashed of t. That would be your first derivative vector, right? The vector that you shoot off to your death. Isn't the guy that we're doing just basically the same vector? Only one difference. His length is 1. Can you see how that might standardize the answers? Because then everybody would have the same version, I guess. Are we go with it? Right. So it's
how you accidentally pick the prime number. That's pretty impressive.
You picked a nice number?
No, you picked the prime number. 317 is prime. That's why
Oh,
we
no,
can't factor any further.
That wasn't me picking it. That was coincidence. That was just luck or bad luck. The fact that it is a prime means I couldn't do anything with it. Of course, you're right.
Yeah, I was trying to figure out what could be done with it if it's prime. So,
well, let's pick one that's got their numbers. Hopefully, I'll get a better version. So this is question 7, and we're getting a space curve. And in question 7, it's a nice polynomial, but I'm assuming that they have played about with the numbers to make it a little bit more user-friendly at the end. So there's a guy. And we are being asked here to find r dashed of t, r dashed of 3, the magnitude of r dashed of 3, and t of 3. Actually, isn't that just asking us to find this guy? Because you need to find all these guys to get it. So I guess that's how it's phrased. Right. Of course, I didn't leave enough room, but that's fine. We'll figure that out. If you differentiate this guy, you get 2t, take away 1. Differentiate this guy, you get 3. And differentiate this guy, you get t squared plus t. The value of this derivative at 3 is 6 take away 1, which is 5. 3, 9 add 3 is 12. And I've screwed up. Oh, no.
I think the derivative of the first one is 2t minus 2.
Oh, thank you. I've screwed up then. And that guy gets you 4. Ah, that is nice. Because the magnitude of that one, which is why I was looking, because it didn't look very pretty. And that's 169. There.
Root 13.
Yeah. Well, 13 is square root of 169, yeah. And so this fella is 1/13 of that guy. Yeah, and that's why you should pick questions from the book, in this case from WebAssign, because don't you get pretty answers? Now, if I gave you any question in the universe, wouldn't you just differentiate it to get this guy? And, you know how you differentiate, right? Well, there's nothing really that you can't differentiate that we'd expect you to do. Then you plug in whatever the number is, in this case is 3. You get the magnitude of this, and don't you put these together to get that guy? So let me jump to another one of those questions. But this one's got all ugly pieces to it. And this is a version of question 8. And the space curve is the inverse tan of t, 2e to the 3t, and 18t e to the t. We're being asked to find the unit tangent vector at 0. So I'll find the derivative. Okay, this will get some cobwebs moving. Derivative of the inverse tan function. Oh, come on, you know the answer. You're just too shy to tell.
1/t squared plus 1.
That's the guy. Now, this one's a basic chain rule. That's why there's 6 of them. And isn't this one going to be a product job? 18t e to the 3t. So if I do an f dashed g plus f of g dashed, you can check on that, but that's what you get. Now, since I'm interested in the answer at 0, I'll find the value of the derivative vector at 0, and that's 1, that's 6, and that's 18. So far, so good. Now, I need to know the magnitude of this vector, which is 1 plus 36 plus 18 squared. So what we got, 18 squared plus 6 squared plus 1 squared is 361. And I think that's going to be a good. Now that took some moving these numbers, didn't it? But it's a perfect perfect answer. It's a 19. So the unit tangent vector at 0 is 119. The derivative vector at 0. So what do you get? 119, 6/19, 18/19. Kind of going through that pretty quickly. But isn't there a flow to these where you really just do the same thing all the time? Don't you take the derivative, plug in the given value of t, find the magnitude of the derivative vector, and then boom, right? You got your unit tangent. Now, as long as you can do the differentiation step, isn't there is pretty much okay. Now, they've been really good with the numbers, but I guarantee you're going to get the square root of 137 sometimes, right? You're just going to get some really ugly square roots. And, you know, so your answer's ugly and, you know, move on. It's a trig one, but there's nothing really ugly on that one. It's a trig one. Okay, I better do a trig one of some kind. Let's do a 10. And the function, the vector function, is a cosine of t and 8t and a 2 sine 3t. We're being asked to find eventually the unit tangent at 0. But it's one of those questions where they tell you to find the derivative. I mean, they tell you to find all these guys, right? Right? They say A, B, C, D. So I'm just going through it as if that's what was being asked. So the derivative, what do you get if you differentiate a cosine? And the reason I'm asking that is to make sure you've got your right hat on. The derivative of, say again?
Negative sign.
Yes, negative sign. And 8. And this guy is cosine of 3t. What multiple will you get when you differentiate 2 sine 3t? What multiple of cosine 3t do you get?
6.
Yeah, 2 times 3. So nobody fell for that one, right? At 0, which is a pretty common number. Sine of 0 is 0, 8 is still 8, cosine of 3 zeros is still the cosine of 0, so you get 6. The magnitude of this vector is the square root of 100, because I'm skipping by that. And the unit tangent vector then at 0 is 1/10 this guy, which means 0, 4/5, 3/5. Shouldn't you always simplify fractions down if you can? Okay, I was really, really fast in that one, but would you agree the numbers are nice? Everything's pretty easy to deal with. You could fill in the gaps yourself if you feel a little bit rushed on that one. We should try this one, only because it's got one little idiosyncrasy in it. It's a t cubed, nothing plus 1, nothing that weird. 4t minus 7, nothing that weird. And a 7 over t. And we're being asked to find the unit tangent vector at the point with coordinates 2, -3, 7. I don't want to know the point. I want to know t, don't I? I need
Roll
to
those in
know.
and solve for t.
Right. So which one do you want me to solve for t?
T is equal to 1. You could put it in for any of the values though.
Right. Would you agree it's 1?
I did 1/7, but I mean 7/1.
Okay, so if you match the z's, 7/t equals 7, 7 equals 7t, t equals 1. Can you do that one? If you wanted to do the x's, wouldn't x cubed plus 1 be 2? 2 cubed would be 1. T would be 1. Well, I mean, it would have to be, wouldn't it? It would have to be 1 all the time. So they could have made that more interesting. Couldn't they have made it so it wasn't one that you could do in your head, but you had some algebra to do? Can we just pretend for a minute that they did a harder version of this one? And when you match the x's, let's say it was a quadratic, you get t equals 7 or t equals 2, right? You get two choices. Wouldn't you have to move on to the middle one to see which one of those two choices it was? Because if it's going to work, doesn't it have to work for x, y, and z? So, you know, be aware of that. That was the first major little kink. Differentiate this guy, you get 3t squared. No biggie with that. Differentiate that, you get 4. What's the derivative of 7/t? That's the other kink, the little kink in this one. 7 over
Well, that's the
t.
same as the derivative of 7 times t to the -1. So it'd be negative 2 over t squared.
Almost. -7. The 7's still
Oh,
there.
times 7.
Right. Now we can do the value of the derivative at 1. So that's 3, 4, and -7. Now we can get the magnitude of it at 1. And that's going to be 3 squared, add 4 squared, add -7 squared. And they're telling me, because I can see the answer over here, that it's the square root of 74. So the unit tangent vector at 1 is that fella, 3, 4, -7, which we will now call that fella. And I'll break the style point rules. Technically shouldn't have rationalized the denominator. Would you agree? Would you also agree that it probably looks just as ugly if you did that as it does right now? So it's probably not going to benefit anyway. So kind of pausing, what have we learned today? There's a new guy in town called the unit tangent vector, and we've learned how to find its value. That's pretty much all we've done so far. You feel comfortable about the process? Right. See what else we can do. That's just a trig one, nothing interesting there. Oh, okay. We have a pretty boring space curve. And we are being asked to find that guy, unit tangent at 1, second derivative guy, and the cross product of the first and second derivative. Wow. Really quite a big mixture, isn't it? Oh, I'm going to add another one. Let's do a dot product as well. Just to keep our hand in dots and cross products. Right now, there is no reason you would expect that this cross product, or for that matter, this dot product, would be anything useful in the movement of an object in 3D space, right? That it told you something that would be interesting to know. But strangely enough, they do. But that's for a different section. Right now, it's just pure algebra. So I'll start off with the original function again. At least the guy isn't that bad. If you do its derivative, you get 8t to the 7, a 1, and a 2t. Now to get this guy, won't I need to find the magnitude? Even although they didn't ask me to, I still need to. Oops. At 1. So let's find this guy at 1. So that's going to be 8, 1, 2. Now I can get the magnitude at 1. That's what I was thinking about. So it's going to be what? 64 add 1 add 4, which is
69.
the square. Say again?
Square root
69?
of 69.
Agreed. I don't think anything interesting you can do with that. So the unit tangent vector at 1 is just going to be that guy over that. To save an entire line of working, can I just cut to the chase and just write the answer down? Are we happy? That's pretty standard. Nothing really going on here. None to see. Now let's continue to here. If you want to get the second derivative at t, you have to return here and you just differentiate it again. You get that guy. Are we cool? Now I want to find the cross product of the first and the second derivative. So it's going to be I, j, k. And this guy isn't these guys, it's this one, right? It's t, it's this one. So it's a t to the 7, 1, 2t. And the second derivative is this guy. And the answer is going to be so many i's, take away so many j's. Hopefully I left enough room. Plus so many k's. Right, if you cover this guy up, you get 2 take away 0. So that's 2. If you cover this guy up, you get 16t to the 7. Take away 112t to the 7s. So 16 take away 112 is negative 96 t's to the 7. And if you do this guy, you get nothing, take away this fella, so you get negative 56 t to the 6's. So it's a 2, it's a positive 96 t to the 7, and it's a negative 56 t to the 6. It's not very pretty, but that's what they asked for. Are you comfortable about how we calculated the cross product, even although it didn't have numbers, it had t6s and t cubes and whatever? Excuse me. And this added one is the dot product of the first and second derivative. Okay, so first derivative is this guy, so 8t to the 7, 1, 2t. Dot product with this guy, 2. No, it isn't. I'm looking at the wrong place. This guy, 56t to the 6, 0, and 2. So it's going to be 8t to the 7s times 56t to the 6s plus 1 times 0 plus 2t times 2. Again, just horrible expressions. 56 times 8 is 448 t's to the 13. That's nothing, plus 40. So if I give you a space curve, r of t, are you comfortable that you could find a unit tangent vector at 1 or 21? Right? Could you find the first and second derivative, r dash t, r double dash t? Could you find the cross product of those two things? Could you find the dot product of those two things? This is really a skill building section, isn't it? They're just getting you to do stuff for no particular reason yet, right? They're just saying, here's a space curve r of t. find these things, right? Find t of 1, find cross product of the first and second derivative. Any questions? Okay. Let's do, who shall we do? Okay, let's do this one. Version 14. We have a space curve. It's e to the 5t, e to the negative 6t, and 1. And we are being asked to find r dashed of 0, the unit tangent at 0, the second derivative at 0, and the cross product of the first derivative with the second derivative. Very similar to the one we just did, but have you noticed that everything now is at zeros, right? At t equals 0. Okay, start off with r dashed of t. Now, if you differentiate this guy, you get 5e to the 5t. If you differentiate this one, you get negative 6e to the negative 6t. If you differentiate number 1, you get 0. Okay, you want r dashed of 0. You get 5e, that's 5, negative 6, that's negative 6, 0. In order, so that's basically the answer done, right? Now, if you want to get this fella, you need to find the magnitude of this vector. (36) and 25 gets you 61, so that's not very interesting. And now we can get the unit tangent vector at 0. It's going to be this guy divided by that. So it's 5 over the square root of 61, negative 6 over 61, and a 0. And that's going to be that fella. Now the next one is the second derivative at 0. We have to start with this version first, find the second derivative, and then later on plug in 0. So the second derivative using this fella, well, it's going to be just multiply another 5. So you get 25 of these guys. If you do this one, you get positive 36 of that guy. And differentiate this guy, you get 0. And so if you want the second derivative at 0, don't you get 25, 36, and a 0? And that gets you the answer. I'm not going to do the last one. That's the last one. Won't I basically just take the first derivative, cross product with the second degree, and you get the usual, right? That's just number crunching. Okay, let's pause again. If I give you a space curve, can you find first and second derivatives? Can you find cross products of first and second derivatives? Can you find unit tangent vectors with a t or with a number? Can you find first and second derivatives with a t or with a number? Can you get cross products with a t or with a number, right? Just skill building. Right? You feel, so if I gave you r of t, you could do any of those things I just mentioned. You feel comfortable with that? That's where we are, right? So let's move on and do something different. Suppose I give you a space curve and I ask you to find the equation, the parametric equation of the line. So imagine that we have a space curve and I want to find essentially the classic Calc 1 question. Remember in Calc 1, you were asked to find the equation of the tangent line. let's find the equation of the tangent line to a space curve. So here's our R of t. And let's suppose at this point here, P, we have a tangent line, right? Okay, it looks like that. Technically, that line goes like this, doesn't it? It's a tangent line. And I would like to find the equation of that tangent line. So the one that we're doing is question 15. And they are telling you the equation of the space curve in its parametric form. Okay, and they're also telling you the coordinates of P, which is nice of them. I tend to write things in vector function format. So are we okay with saying, look, that is the same thing as this? Is that obvious?
You look like you wrote 6 root t. Or, is it 6 root t or 6 root 6?
My t's look like 6's, and my 6's looks like t's. It's 6 root t. I'll do it again. T squared plus 1, 6 square root of t. There. Looks much more like the thing. There, that's the guy. I need to know 2 things to get the equation of that green tangent line, don't I? Don't I need to know the coordinates of a point on the line? Oh, wait a minute. Didn't we get that for free? I know the point. It's 2, 6, -1. What's the other thing that you need to get the equation of a line? One is the point, done. What's the second thing you need to get the equation of a line?
The direction vector?
So I need to find the direction vector, which I typically call V. Great. Now, isn't the direction of that line the same thing as its first derivative vector? Agreed? So isn't the direction vector that guy, right? At this point. Oh, that's a bit annoying. What value of t do you need to generate this point?
1.
Correct. Wasn't the choices actually 1 and -1 unless you picked the right one to start with? Let's
That's true.
pretend, yeah. If I started with t squared plus 1 equals 2, wouldn't t squared have to equal 1? But wouldn't that give me 2 choices? It might be +1, it might be -1. But when I chose the middle one, would you agree there wasn't a choice? It was 1, right? That was the only one that worked. Right. So you tell me that, but I need to know him. So to find the direction vector, I just find the first derivative at whatever t is, in this case 1. So the derivative, let's say r there, is differentiate this guy, you get 2t. If I want to differentiate this guy, won't I call him t to the half? And if you multiply by the power and then you divide by the new power, he ends up looking like that, which I'll come to. And if you want to do this guy, you get e to the t squared take away t, but it is a chain rule. So don't you have a 2t minus 1 thing going on?
I might be wrong, but didn't you drop a divided by 2? Shouldn't it be 3/2 t in the middle?
That would be if you had your integration hat on, but we're differentiating here.
Oh. Also, where did the 6 go? Oh, no, I see it.
Well, a half and 6 became the 3.
That was what I did wrong. I forgot the 6, and so I then lost the half of it. What?
Gotcha. I'm just rewriting this guy. I'm not sure it's worth it, but I'm rewriting them to look pretty. So we want to find the derivative at 1. Keep doing that to my poor R. There we go. Let's try this a third time. At 1. 2 lots of 1 get you 2. 3 over the square root of 1 gets you 3. If you plug in 1, that's 1. If you plug in 1, that's 0. E to the 1, you get 1. We have just found R dashed of 1. So I now know my direction vector. I also know my point. Now I want to get the equation of the line. If I do it in vector notation, it's going to be 2 plus 2t, then 6 plus 3t, then -1, add a t. And if I want to do it in parametric form, you do in Weber sign at least, a curved bracket, 2 plus 2t, 6 plus 3t, and -1 plus t. Technically speaking, that's not parametric form, but Weber sign makes you write it that way. If you really wanted to do it as a proper parametric form, wouldn't you write it down as 3 separate equations?
Where did that -1 come from at the end? Like the -1 plus t?
-1, don't know, let me check it. Oh, it came from that -1 here on the point P.
Oh, okay, I see it.
So 2, 6, and -1. There's where the 2 came from. That's where the 6 and the -1 came from. The 2t, 3t, and 1t came from 2, 3, and 1 here. And that is how you find the classic equation of a tangent line in 3D space. So far, so good. Probably they don't do this, but they might. They have computers on jets. Can you imagine a jet doing that kind of maneuvering that they do in 3D space, right? Because they don't want to get shot down. Can you imagine that at any given point, if you fired your rocket and it wasn't one of the clever ones, right? Just the rockets that go in straight lines, wouldn't this be the equation of the straight line that that rocket would travel at? And if you followed its path, you would eventually figure out where it hit. So if you were firing an unintelligent missile, in other words, the direction you fire is the direction it goes, you could imagine, at least initially, what it would be doing in space. Where are we going? That's 15 done. 16's basically the same idea, but with an uglier function. Okay. Do I want that one? Probably not. Okay. Now, I guess I should do one more. I'm jumping ahead too quickly. Okay. As a version of question 17, we have a space curve which I'm already rewriting as e to the -5t, the cosine of 5t, e to the -5t, sine of 5t, and then e to the -5t. We are being told that it passes through the point with coordinates 1, 0, 1. And first question they ask us is to find what t is equal to. Right, if you do the matching here, e to the -5t cosine 5t has to be 1. Well, that's kind of hard to do. E to the -5t sine 5t is 1. I'm going to use that one. E to the -5t, the sine of 5t, right, like combination there, equals 0. Any suggestions for a value of t that would make that happen?
1/5.
No, but I know why you chose it. You're thinking make that one.
0, right?
Yeah. I want e to the 0, sine of 0, get you 0. But check it out. If you plug 0 in here, don't you get e to the 0 cosine of 0, which is 1 times 1 checks. At this end guy, if you make t equals 0, isn't e to the negative 5 zeros still e to the 0, 1? Do you see that that guy is the t value that generates 1, 0, 1? Now, some of you might be thinking, well, wait a minute. Couldn't I also get 0 if I made 5t pi or 5t 2 pi or 77 pi? Well, yeah, you could make the middle one 0, but it wouldn't work for either of the two end ones. Now, if I chosen the last one, I would have had that. Would you agree that t equals 0 also works? What power of e, sorry, 1. What power of e gets you 1? Oh, e to the 0 gets me 1. So negative 5t equals 0. So t equals 0. Do you see that even a simple thing like what value of t gets you that point can have its own little idiosyncrasies, right? Things you have to figure out. And that wasn't even the major question. That was just question A, I guess. Now, finding r of t is a pain in the butt. Won't you have to do a product rule? Won't you have to do a slightly different product rule, including chain rules? And won't you have to do a product rule? And I am going to cheat because I don't want to do this. You know, it's e to the negative 5t, 5 sine 5t plus 5 cosine 5t. And that's just for the first guy. If you do the middle one, you'll get e to the negative 5t, 5 cosine 5t, take away 5 sine 5t. And if you do the last one, it's the only one that's actually any good, is that one. Can you just trust me that you're going to have a product rule with some chain rules going on, product rule with some chain rules going on, and this is the mess you got. Otherwise, we'd be spending 20 minutes just doing that. And now we are going to find the direction vector. It's going to be the derivative at 0. And as ugly as all of that looks, it doesn't actually come out to be anything anywhere near as bad as that. It's negative e to the 0 times nothing plus 5, comma. E to the negative 0 is just 0. 5, take away nothing. And negative 5 e to the 0. So we end up with, that's negative 1, negative 5, middle 1, 5, end 1, negative 5. So I have the point with coordinates 1, 0, 1, and the direction vector that looks like that. So the equation of this tangent line will be 1, take away 5t, 0, add 5t, and 1, take away 5t. Finished. Okay, that would have taken you forever in a day, but once you got through that, the rest is pretty straightforward. So if I gave you a space curve r of t, and I told you to find the equation of the tangent line at the point P1, 2, 3, do you feel comfortable about the process? you're going to take the coordinates of the point and figure out what t value makes that happen. You're going to differentiate the function and plug in that t. That gives you the direction vector, and then you put them together and you're finished. Oh, we have to try this one. It's so cool. I don't want to wait till tomorrow because I'll forget. I have two space curves. They're using the same parameter t, which is a bit weird. And they intersect. So, making no attempt to be accurate, can you imagine this is R1? And can you imagine that this is R2? In fact, couldn't we put them into that software and actually really look at them? But can we pretend that's those two guys? And they intersect here. They actually tell you the coordinates of where they intersect, but let's go hunting for it. What do you know about these two space curves when they intersect?
They equal each other.
They do. So doesn't that make the X, the Y, and the Z all equal each other? Now, when I look at the R1 and the R2, would you agree the Z coordinates are the best ones to match? So the Z coordinate of one has to equal the Z coordinate of the other. Now, if you rearrange this one a little bit, you're trying to solve that. If you pull out t as a common factor, you're going to get that. Now that gives us three solutions: 0, +2, and also -2. We'll assume that this space curve only intersects at one point. How do I find out which one of those is the one I want, the one I need?
You plug it into the X or Y, right?
Yeah. If I plug 0 in, it matches. So, can you trust me? Sine of 0, 4 zeros. Sine of that, 0 squared. Check. If I plug in 2 here, does A equal sine of 2? No, doesn't match. If I plug in -2, will negative A equal the sine of -2? It doesn't match. Do you see how I decided from 3 choices which one actually was the one that I needed? Does that make sense? Right. So what we're going to do here is not find the equation of a tangent line, but can you imagine that these 2 points, when they cross, they make an angle theta? And we're being asked to find the angle of intersection. Find theta. If you take the derivative of the first one, you get 4, 2t, 3t squared. And if you find the derivative at 0, you get the direction, which is 4, 0, 0. So that's the direction vector of the first curve. If you then take the derivative of the second one, which is this guy, you get cosine t, 3 times the cosine of 3t, and you get 2. And if you plug in t equals 0 to this one, you get its direction. The cosine of 0 is 1, that's 3, and you get 2. Won't theta then be the angle between 400 and 132? Basically, you find the derivative vector, right? And that tells you the angle at which the curve is meeting each other. And one of them is this vector and the other is that vector. So is it the angle between the two vectors, the angle that they intersect at? How do you, I'm not finishing doing this, but how do you finish that off? How do you find the angle between two vectors? Because we've done that earlier, like weeks ago. You're saying something, but I didn't hear you, Molly. How do you do it?
I was thinking dot product, but that doesn't make sense.
Oh, go back, it does make sense. Dot product works perfectly. The cosine of the angle between them will be the dot product of their magnitudes. Okay, the dot product is 4. The magnitude of this guy is 4. And the magnitude of this guy is 9, 10, is the square root of 14. Theta, the angle you're looking for then, well, we have done it, is whatever that ends up being. Actually, that simplifies down to 1 over root 14. It works. Why did you talk yourself out of it, Molly? You thought it didn't make sense. What was the thinking? What stopped you doing it?
I forgot about the cosine theta piece.
Ah, okay. So you remembered this, but then you said, well, what?
I thought
Yeah. I'm stuck.
magnitude of 4 would be 16. Is that not right?
Is that because I can't count? You think this is a 16? Is that what you said? It's 14. But it's worth checking because you know I can't count. 1 add 9 add 4. Yeah, 14. That's us, guys. Oh, say your last name and bye-bye.